In this video, I'm going to discuss magnetic force exerted on the moving charge, electric charge. In this video, I'm going to discuss magnetic force. In this video, I'm going to discuss magnetic force exerted on moving electric charge. We know that there's a magnetic force when you have a magnet. Then you have a magnetic force on a magnet. But in the last lecture, we have discussed that it is actually the magnetic field can be generated from moving electric charge. So the source of magnetism is not the little tiny magnet, but it's actually generated from the moving electric charge. So now here, there is a magnetic force actually can act on moving electric charge. So I keep saying it's the moving electric charge. We're not gonna, if you have a stationary charge, if charge is not moving, there is no magnetic force. It doesn't do anything, no magnetic force. This charge has to be moving in the external magnetic field, then this charge will feel magnetic force. And so the motion matters, and the direction of motion relative to the magnetic field matters. If you have a electric charge that's moving parallel to the magnetic field, then this moving charge won't feel any magnetic force if it's parallel. It feels the magnetic force maximum when it's moving perpendicular to the magnetic field. Again, if it's stationary charge, no magnetic force on the charge. And then if it's moving, but if it's moving parallel to the magnetic field, no magnetic force. Oh, magnetic force, if it's it has some kind of a perpendicular component, the perpendicular component of the motion to the magnetic field feels the magnetic force. So therefore, the maximum magnetic force it's going to feel is going to be perpendicular to the magnetic field. How does the magnetic force applied on a moving charge? It's going to be perpendicular to the plane of a magnetic field and the motion of an electric charge. So this electric charge, again, it's going to feel the magnetic force perpendicular to its motion. Let me show you on the note. So magnetic force on a moving charge. Again, no magnetic force. When electric charge at rest. So you don't see it in electrostatic, only in electrodynamics. So let's see, I'm going to do my best to draw the magnet here. Okay, magnet. So here I'm going to do the U-shaped magnet. Let me think. more like this side. Oops. And then this one should something like this. So let's say south and north. This is going to be the south and this is going to be north. So the magnetic field is coming out from north to south. This is going to be the magnetic field, right? Let's see, moving electric charge. So I'm just going to shoot the electron. Electron beam, what color would that be good? Yellow. Electron beam is coming in this direction. So when you have electrons that are coming that way, you do not have to 100% memorize it, but I want you to know the relationship. So again, we're going to use, I'm sorry that I use the right hand rule again, but it's not the same right hand rule. So you're going to use the right hand. So here's the right hand. Then, okay, so direction of your fingers, right hand fingers. This is the current. Current. So remember, current is defined as a E plus, the positive charge. Then the direction of your palm. So I have a right hand, you guys have right hand, and then direction of your palm. So you can kind of bend your finger now. After you do it, direction of your palm is going to be the direction of magnetic field. Magnetic field into this way. So if you were to curl up your fingers like this, and curl up your fingers, that's going to be the direction of magnetic field. This is going to be the direction of magnetic field. This is then the direction of your thumb. That's going to be the thumb. It's going to be the direction of force. So let's look at this example. Okay, just make sure you can see it, right? Right hand. Direction of your fingers is the direction of current, positive charge. Direction of a thumb, it's going to be the direction of your magnetic field. And then direction of a force applied on a moving charge is going to be the direction of your thumb. Okay? So then let's look at this example. We have, let's see, here, it's better. Is it pointing in the same direction? No, it's this way. So it's this way. No, it's this way. Are they? I can't tell. So you got to do it. If you use your right hand, the direction of your palm should be coming north to south. North to south. North to south, right? Then electrons is going to be the direction of your finger, but coming out. But this is electron, which is negative charge. So the current is actually pointing in opposite direction. What does my direction of my thumb? It's going to be upward. So In this case, the force is applied upward. I'm going to draw it like this. So electron beam coming out, right? Electron beam coming out. And magnetic field in this direction. Then the force is coming, applied on the moving charge upward. It's because you gotta reverse the direction of E plus. This is gonna be the E plus, the current. All right. So here, magnetic force is applying only on the moving charge, electric charge. You can have a magnetic force on the electric charge when the electric charge is moving. And let me see how the magnetic force is applied. Magnetic force is perpendicular to how the magnetic force is applied. It's a perpendicular to the motion of charged particle. So that means that if the force is applied perpendicular to the motion, right? So that also means that acceleration is perpendicular to the motion of moving charge. If the acceleration is perpendicular to the moving charge, then what happens to its speed? Do you see any change in its speed? How about its direction? Acceleration is perpendicular to the motion, means that there's no change in speed. Only its direction is changed. So you can only do it to deflect the electron beam or any charged particle. And you're going to see that this force is the greatest when the moving charge charged particles, which is also current, right? Current carrying wire, is perpendicular to the magnetic field. That means force is 0 when the charged particle move parallel to the magnetic field. Also, when you flip the current in the opposite direction, force also reverses. Flip. When you have, let's see, what was the color I was using? Orange. The current, right? And magnetic force is the magnetic force. Magnetic field. Magnetic field is in this way. Then current coming, magnetic force is going to be upward. What color is the force? Blue. Force. This is going to be the maximum. But if you have a current that's running, same direction as the magnetic field, then the force is 0. In the case that's, and then if you flip the direction of a current, I, and the magnetic field is this way, looks different. Then the force will be down. So make sure you get all of these. That's the magnetic force. I can show you the. So you see the magnetic force on the current carrying wires. If you have a current that's running in this direction, which direction in this case that a magnetic field is applied? So it's a magnetic field is applied perpendicular to the current. Then you're going to have a perpendicular to wire. Then you're going to have a strongest magnetic force. And depends on the direction of a magnetic field relative to the current, you may have up or down, forces up or down. Magnetic force on a moving charge. Moving charges in a magnetic field experiences deflecting force, which means it's just only changing its direction. Greatest force is applied when particles in a perpendicular to the magnetic field lines. The least force is when particles move other than a perpendicular to the magnetic field, and no force at all when particle moves parallel to the magnetic field lines. So in this case, the same example actually I just did. Electron beam is coming. So you gotta put your finger, flip it into it, north and south, force is gonna be upward. Magnetic, this is electron beam, so the current is in the opposite direction, your direction of your finger, direction of your palm, and then the direction of your thumb. So this magnetic, using this, we can also see some application. How about electric meter? You can put the compass needle in the coil to see if you have any current that's running. This is going to deflect the compass needle inside the loop because the current carrying loops will generate the magnetic field, and it's going to deflect the needle. So you can check to see if you have any current running by using this device. And then when you make this device even more sensitive by increasing the number of turns, you can even make an amp meter or voltmeter, which is called galvanometer. Also, implementation to this is galvanometer, right? You can measure the amps, the current, or you can measure the voltage. Electric motor, you can even also apply this magnetic force applied on the current by making the current loop, and then you can rotate it. So converting electrical energy into mechanical energy by using the magnetic force. How would you do that? Is that you just connect to the plus and minus, then the current will run. So on this side of the loop, current is going forward. On this side of the loop, current is coming backward. So depends on the direction. The force is going to apply either up or down. So you have a force that's applied. So on this direction, current is running in this direction, right? And then a magnetic, using the right hand, let's say magnetic field is applied in this direction, then it's going to go down. This side is going to be current is up, magnetic field is, what did I say? Current is up and this, and then it's going to go down on this side. But here, current is going down, field is, and then what did I say? Field is this way. So it should be coming in this way, up. So down and up. But what's smart thing about this is that there's a slit. So typically when you have an up and down, unless you change its direction of a current, it's just going to stay there. But since you make this little slit, so when it rotates 90 degrees or 180 degrees, it changes the plus and minus. It gets I equals 0 for that moment, and using the momentum, it's going to keep rotating and it becomes I minus 0. So it swaps the direction of a loop current, and then it just keeps, so initially it was down, it becomes up, and then it down and up. So you can change the direction of force on the one loop to the other, one side of the loop to the other side of a loop. So this side is going to be up, down, by rotating. So it continuously rotates. So that's electric motor. Electric motor is that you have a current carrying loop that's in a magnetic field, and then it rotates. And actually you're going to see that electric motor and electric generator is going to be the same mechanism. But anyhow, so this is the end of this talk. It's a magnetic force on the moving charge. Again, make sure you get all the punchline. So the punchline is here, magnetic force on the moving charge, right? Magnetic force applies perpendicular to the motion of the moving charge There's no magnetic force when the charge is not moving, and force is greatest when the moving charge in the magnetic field is perpendicular. There's no force when they're parallel or anti-parallel. All right.